All right, hello everyone, and welcome to lesson 6.5, which is on energy of phase changes. Today, our learning objective is to explain changes in the heat absorbed or released by a system undergoing a phase transition based on the amount of the substance in moles and the molar enthalpy of the phase transition. So, we are looking at how energy is interacting with these particles when we are undergoing different phase changes and what that means in terms of energy absorbed and released when we are dealing with complementary phase changes. So let's start off with an idea from our last lesson, which is specific heat. So if we're looking at a phase change of water going from solid to liquid and liquid to water vapor or gas, I want you to think about why the specific heat of liquid water is much higher than the specific heat of ice or water vapor. Now, in liquid water, molecules are closely packed and they are continuously forming and breaking hydrogen bonds. Now, if we are adding heat to liquid water, a significant portion of that heat energy is going to be used to try to disrupt those intermolecular attractions rather than increasing the kinetic energy of the molecules. So that means that more energy is required to raise the temperature of water by 1 degree Celsius than compared to that of a solid or gaseous state of water. Now, in ice, the hydrogen bonds are already arranged in that rigid, ordered crystal lattice. And because the structure is more fixed, there's less energy needed to increase motion. So the specific heat is going to be lower than liquid water. And then finally, in steam or gaseous water, the molecules are really far apart, and so they have very weak intermolecular forces, so little energy is needed to increase their kinetic energy, which means they have an even lower specific heat than solid. This is an example response that you could give that kind of sums up what we did on the last slide. So essentially, liquid water is going to have a higher specific heat because of its extensive hydrogen bonding. When heat is added to liquid water, a lot of that energy is going to be used to break and rearrange hydrogen bonds rather than increasing the average kinetic energy. So more energy is required to raise liquid water by 1 degree Celsius. And here is just a nice explanation of what's happening in each one of those particle level diagrams. So we have our hydrogen bonding in liquid water, we have our crystal lattice type structure with ice, and then we have our molecules that are farther apart in gaseous water. All right, so that previous example sets us up perfectly to understand the exothermic and endothermic processes within a phase change diagram. So let's continue thinking about water. When we are going from solid water to liquid water, energy has to be put in to break that crystal type lattice of an ice cube into liquid water. And because energy has to be put in order to break those connections, that is going to be an endothermic process. Same with going from a liquid to a gas. If you have liquid water and you have all of that hydrogen bonding, you're going to have to put a lot of energy into those specific hydrogen bonds in order for them to break apart and become its gaseous state. Now, in the opposite way, we have our exothermic processes, meaning that more intermolecular forces between those water molecules are being formed. And when something is being formed, that means we're going to release energy into the surroundings. So when we're going from gas to a liquid, we're going from particles that are really far apart and have really no connection with each other to a liquid where all of these water molecules are now connected via hydrogen bonding. So all of those hydrogen bonds are now forming, and that is going to be a release in energy. And same goes between a liquid and solid. All right, so on the previous slide, we looked at this phase change diagram, and I'm sure you noticed that when the phase actually changed from solid to liquid or liquid to gas, there is a plateau in temperature. So here between a solid and liquid, you can see the temperature is not changing when the phase change is actually occurring. That is something called latent heat. And the reason for that is because before we got to that plateau, energy was being put in to those particles and they were starting to heat up. They were starting to increase in average kinetic energy and they were getting to the point of turning into a liquid. Now, when they got to that point of turning into a liquid, all of the energy is going into breaking those intermolecular forces between the solid particles and letting them turn into our liquid particles, which have more of a free flowing shape. Same goes from going from a liquid to a gas. When we're putting heat into this liquid, we are increasing the average kinetic energy of those particles. However, when we get to the point where they're actually changing over into a gas, all of that energy is going into breaking the hydrogen bonds between all of those particles in the liquid so they can actually turn into a gas. And so when we have that phase change happening between a solid and a liquid, that is known as your latent heat of fusion. It's very important that you know that fusion is between solid and liquid. And then when we go from a liquid to a gas, that plateau there is your latent heat of vaporization. And again, you need to know that. Now, in the curriculum guide, it's stated that the energy absorbed during a phase change is equal to energy released during a complementary phase change in the opposite direction. So if we're looking at, let's say, vaporization, if we are vaporizing a liquid into a gas, we're going to have to put in energy to break those bonds, right? So that's going to be an endothermic reaction. So our delta H of vaporization would technically be positive, right? Because it is an endothermic reaction. Now, if you were given the delta H of vaporization and it asked you to solve for the delta H of condensation, all you're doing is taking the negative of that value, which is shown here in the example. Because condensation is going to be the same amount of energy, however, this time it's going to be released instead of absorbed. And this works the same way with fusion. So if you were given your delta H of fusion, which is going from solid to a liquid, and it wanted to ask you the delta H of freezing, all you would do is take the negative of that delta H of fusion, and that will give you the corresponding complementary phase change. All right, so here is a diagram given by College Board, and it's said to explain what happens at the particle level that makes segment D longer than segment B. So first, let's look at what does it mean by longer? And we can see on the x-axis, it is heating time. So we notice that our heat of vaporization takes much longer to actually turn the liquid into a gas than it does for us to turn the solid into a liquid. Now, this should make sense to you after our discussions about water. We know in liquid water, there are a lot of particles really close together, and there is a lot of hydrogen bonding going on. So it makes sense for D to take a lot longer period of time to actually convert it into a gas because there are so many hydrogen bonds that it has to overcome to become a gas. Whereas with our segment B, the energy that is required to break those intermolecular forces in that fixed solid structure is going to be a lot less because there are fewer attractions that need to be disrupted. So here's an example response to this question. when we are turning a liquid into a gas, which is our heat of vaporization, we actually have to separate the particles from each other. So that's going to take a lot more energy than when we are just taking our solid and breaking that crystal structure. So they're still around each other. They're just not in that solidified crystal lattice anymore. All right, this next example says a 2-mole sample of ethanol undergoes the phase transition illustrated in the diagram above. The molar enthalpy of vaporization of ethanol is positive 38.6 kilojoules per mole. Which of the following best identifies the change in enthalpy in the phase transition shown in the diagram? So we are given delta H of vaporization, which means we have a liquid and it's turning into a gas. Now here in this specific diagram, the arrows are pointing down into the liquid, meaning the particles are entering the liquid phase from the gas phase. And that means we are looking at condensation. Now, condensation and vaporization are complementary phase changes. And remember, the energy absorbed during a phase change is equal to the energy released during a complementary phase change in the opposite direction. So if we are trying to figure out what is our change in enthalpy for condensation, all we're doing is taking our delta H of vaporization, changing the sign, and making sure it is for a 2-mole sample. So heat of vaporization is positive 38.6 kilojoules per 1 mole. And we know we are given 2 moles. So that means our current value for the ethanol is going to be positive 77.2 kilojoules. However, we know that this number value is for delta H of vaporization. We are trying to get the value for condensation, which is the opposite. So we are going to take the negative of this value because it is the complementary phase change. So our answer to this question would be 72.2 kilojoules as a negative value. All right, and then our last example for today, the diagram above represents the melting of water. A 2-mole sample of water at 0 degrees Celsius melted, producing liquid water at 0 degrees Celsius. Based on the diagram, which of the following best describes the amount of heat required for this process and the change that took place at the molecular level? So first thing I want us to kind of discuss here is you can see that it says that we had solid water at 0 degrees Celsius and liquid water at 0 degrees Celsius. That means we're going from solid to liquid and we're at the same temperature, which means we are clearly right in the middle of our latent heat of fusion. And remember, the temperature is not changing even though heat is being added because all of the added energy is being used to break those intermolecular forces, not to actually increase particle motion. So now let's address what the question is actually asking, which is to describe the amount of heat required to actually change our solid into a liquid. Now we are given that it is a 2-mole sample, and we are also given the amount of energy required to get to this point of our solid turning into a liquid. So you can see how these molecules in this sample have those hydrogen bonds, but they're a lot closer together and they're more free flowing. So this is going to be our liquid, and then this is our solid. So since we know that we need 6.02 kilojoules per mole to convert our solid into a liquid, and we know that we have 2 moles, that's going to tell us that we have 12.04 kilojoules needed to actually make this happen. So with sig figs, this answer should be 12.0 kilojoules.